After studying this module, you shall be able to learn about chemical kinetics and chemical dynamics, define rate law and rate constant, define elementary reaction and molecularity, define order of the reaction and stoichiometry, learn about the Arrhenius equation, know about the physical significance of activation energy. In chemistry, we frequently come across two important topics, that is chemical kinetics and chemical dynamics. In fact, chemical kinetics and thermodynamics are very important branches of chemistry. Thermodynamics talks about the feasibility of the reaction, whereas chemical kinetics talks about the speed of the reaction. So, before proceeding, let us first understand the difference between chemical kinetics and chemical dynamics. The term chemical kinetics comprises of two words, chemical and kinetics. Generally, the term kinetics refers to the study of rate of change. The other term is chemical, which indicates that we are studying chemical reactions. In all, chemical kinetics, also referred to as reaction kinetics, is the study of the rate of the reactions and the factors affecting it. It determines the rate of the reaction with respect to some suitable and easily measurable property which changes with time. Chemical kinetics is an experimental science which studies the reaction at macroscopic level. Now, the other term is chemical dynamics, which comprises of two words, chemical and dynamics. Again, the word chemical refers to the study of chemical reactions. In fact, the word dynamics and kinetics are used interchangeably and are considered synonyms in scientific dictionary, and therefore chemical dynamics is closely related to chemical kinetics, but it is concerned with the reactions taking place at microscopic level. Or one can say that chemical dynamics is a part of chemical kinetics, which is concerned with the microscopic behavior of reacting species. The ultimate aim of chemical dynamics is to theoretically calculate the rate of the reaction from the knowledge of fundamental properties of reacting species. Before studying chemical dynamics, it is important to have a good knowledge about the basics of chemical kinetics. So, with this, in the next section, we will first talk about some of the important fundamentals of chemical kinetics. Rate of the reaction. Rate of the reaction at any instant of time depends upon the concentration of the reactants at that instant of time. Let us consider the reaction A going to P, where A is the reactant and P is the product. Rate of the reaction can be expressed as minus d concentration of A upon dt, that is time, where the negative sign implies that the concentration of the reactants is decreasing with time. However, it is important to remember that rate of the reaction is always positive. It can be confusing since the rate of disappearance is negative. However, the rate can never be negative since the rate is determining how fast the concentration changes with time. Similarly, as the reaction proceeds, the concentration of the product increases with time. So, the rate can also be expressed as d concentration of P upon dt. Thus, rate of the reaction is defined as the instantaneous rate of change of concentration of any of the reactants or products at that time. Since rate is defined at any instant of time, it is also referred to as instantaneous rate of the reaction. Now, let us consider another reaction of the form A of A plus B of B giving C of C plus D of D. The rate of this reaction in terms of rise in the concentration of the product or decrease in the concentration of the reactant per mole is given as minus 1 upon A d concentration of A upon dt minus 1 upon B d concentration of B dt. For products, we have 1 upon C d concentration of C dt and 1 upon D d concentration of D dt, where A, B are the stoichiometric coefficients of the reactants and C and D are the stoichiometric coefficients of the products. Now, from this we can say that unit of rate of the reaction is concentration time inverse. Since concentration is expressed in moles per liter and time in seconds, so the unit of rate of the reaction becomes moles per liter per second. On the basis of speed of the reaction, that is the rate of the reaction, chemical reactions can be classified as fast reaction, for example precipitation of AgCl, slow reaction, for example rusting of iron, and moderate reactions. These are those reactions that take place in few seconds or hours, for example digestion of food. One must remember that very fast and very slow reactions are ruled out in laboratory exercises. Only moderate reactions are studied in laboratory, for example hydrolysis of methyl acetate. These rate laws and rate equations give the relationship between the rate of the chemical reaction and the concentration of its reactants. According to rate law, rate of the reaction is directly proportional to the product of the concentration of reactants raised to the power of their numerical coefficients as determined experimentally. So, for the reaction A of A plus B of B giving C of C plus D of D, the rate law expression becomes rate equals to K concentration A to the power m into concentration B to the power n. It is important to note over here that the proportionality constant K is the rate constant and is also referred to as rate coefficient, and the coefficients m and n refer to the order with respect to reactants A and B. The order with respect to a component is the power to which the concentration of that component is raised in the rate law, and this may not be similar to the stoichiometric coefficient. Let us now look at the characteristics of rate constant. The rate constant is characteristic for a given reaction. This rate constant quantifies the rate of the chemical reaction. The value of rate constant is environment and reaction specific. It depends on temperature, and for a particular reaction the rate constant is independent of concentration. Rate constant for any reaction is a macroscopic quantity as it can be determined experimentally, and for different reactions rate constants are different. Now let us look at the important terminology of kinetics, that is molecularity and order. Molecularity is defined as the minimum number of atoms, molecules, ions or radicals taking part in an elementary reaction. Elementary reaction is nothing but a chemical reaction in which one or more of the chemical species react directly to form product in a single reaction step. So one can say that molecularity refers to the number of molecules consumed in a chemical reaction. For example, N2O5 giving NO2 plus NO3, for this reaction molecularity is 1, and for the reaction 2H2 plus O2 giving 2H2O, the molecularity is 3. Now it is important to note that for the reaction 2H2 plus O2 giving 2H2O, the minimum number of molecules taking part in the reaction is 3. So the molecularity is 3. However, if we write the reaction as 4H2 plus 2O2 giving 2H2O, molecularity comes out to be 6. But this is not accepted as these are not the minimum number of molecules taking part in a chemical reaction. Molecularity is defined for elementary reactions. It is a theoretical concept, and molecularity is always an integer and can never be 0 for any chemical reaction. It is invariant of the chemical equation and provides no information about the reaction mechanism. Now the other important term is order. The order of the reaction is defined as the sum of the powers to which concentration terms are raised in the rate law expression, as we have already seen. Order of the reaction depends on the mechanism of the reaction. It describes the relationship between rate of a step in chemical reaction and the concentration of one of the reactants consumed in the reaction. For the reaction which we have already seen, A of A plus B of B giving C of C plus D of D, rate law gives the equation rate equals to K concentration A to the power m into concentration B to the power n. These exponents m and n are referred to as partial orders of the reaction with respect to reactant A and B respectively. It is important to note over here that the values of these exponents are not generally equal to the stoichiometric coefficients A and B. This is because order of the reaction depends on the mechanism of the reaction and is determined experimentally. At this point of time, we even need to remember that the rate laws and the order of the reaction are determined experimentally, as these cannot be predicted from the stoichiometry of the reaction. The stoichiometry of the reaction gives the relationship between the amounts of the reactants and the amounts of the products. Thus, it is important to remember that order of the reaction need not be identical with the stoichiometric coefficient of the reactant. Some of the examples that we have are like N2O5 giving NO2 plus NO3. For this reaction, the order comes out to be 1 with respect to N2O5. The other example that we have is 2HI giving H2 plus I2, where the order of the reaction turns out to be 2. As we already know that the order of the reaction is an experimentally determined quantity. The order of the reaction can be integer or fraction and can even have a value of 0, which is not so in the case of molecularity. Order is defined for a reaction as a whole, which might involve one elementary reaction, or it might involve a sequence of elementary reactions. Order of a reaction change with the conditions such as pressure, temperature, concentration and so on. Again, I will highlight over here that the units of the rate constant depends upon the order of the reaction, and the unit of rate of the reaction is always concentration upon time, irrespective of order or rate constant for a particular reaction. With this background of fundamental knowledge of chemical kinetics, let us now move to the factors that affect the rate of the reaction. The rates at which the reactants are consumed and products are formed vary from reaction to reaction. Some of the important factors that affect the rate of a reaction are concentration of reactants. The rate of the reaction increases when the concentration of the reactants increases. Nature of the reactants. The number of reacting species, their physical state, the complexity of the reaction greatly affect the rate of the reaction. Reaction that involves the breaking of chemical bonds or the rearrangement of molecules commonly are slower than the reactions that involve simple combination of two ions of opposite charge. Another factor is catalysts. Catalysts are the substances which affect the rate of the reaction without actually taking part in the reaction. They increase or decrease the rate of the reaction. The catalysts that increase the rate of the reaction are called positive catalysts. For example, reaction between H2 and N2, that is hydrogen and nitrogen, occurs in the presence of iron as a positive catalyst to form ammonia. The catalysts that decrease the rate of the reaction are called negative catalysts or inhibitors. For example, acetanilide acts as a negative catalyst in decomposition of hydrogen peroxide. Another important factor is pressure. On increasing the pressure, the reactants come closer to each other. Therefore, the frequency of collision increases, thereby increasing the rate of the reaction. The effect of pressure occurs only for gaseous molecules. The reactions involving liquids and solids are not affected by change of pressure, since liquids and solids are highly incompressible. Another important factor is temperature. Chemical reactions proceed faster at higher temperatures. For example, food cook faster at higher temperature than at lower ones. We use a burner in laboratory to increase the speed of the reactions that proceed slowly at ordinary temperatures. Another important factor is radiation. Photochemical reactions are faster than the thermal reactions because in the former all the energy of the photons is completely used in exciting the molecules, whereas in thermal reactions the energy is distributed at random into translational, rotational and vibrational modes of motion. Last but not the least, the factor which affects rate of the reaction is surface area. Except for gases or solutions, the reactions occur at surface or interface between two phases, and therefore the rate of the reaction between the two phases depend on the surface contact between two phases. Finely divided liquids and solids, because of greater surface area, react more rapidly, and hence we can say that greater is the surface area, faster is the reaction. With this discussion, let us now move to Arrhenius equation, which is the empirical relationship between rate constant and temperature. Arrhenius equation. In 1889, Arrhenius developed a relationship between rate constant of the reaction and temperature based on experimental investigations. Arrhenius measured rate constant at different temperature for a particular reaction and plotted ln k versus 1 upon T, where K is the rate constant and T is the temperature, and we get a plot like this. which is nothing but similar to a straight line y equals to mx plus c, where m is the slope and c is the intercept. From this we get the equation, that is the Arrhenius equation, as ln k equals to ln A minus Ea by RT. This equation is Arrhenius equation of activation energy. This equation can also be written in the form as k equals to A into exponential minus Ea by RT, where A and Ea are constant characteristics of the reaction and R is a gas constant. Ea is Arrhenius energy of activation, which is the minimum access energy that the reactant molecules must have in order to react. The unit of activation energy is usually expressed in kilocalories per mole or kilojoules per mole. Now, the other important characteristic is capital A, which is pre-exponential factor or Arrhenius exponential factor. The unit of pre-exponential factor is same as that of rate constant, because the exponential term minus Ea by RT is a dimensionless quantity. Both these pre-exponential factor and activation energy are called Arrhenius parameters. According to Arrhenius equation, the rate constant increases exponentially with temperature. So, low activation energy means a fast reaction and high activation energy means a slow reaction. The rapid increase in K with increase in T is mainly due to increase in the number of collisions between the molecules whose energy exceeded the activation energy. With this, let us now have a look at the physical significance of Ea. Ea in Arrhenius equation is referred to as energy of activation. It is important to note that products are formed only when the reactant molecules come close and collide with each other at one and same time. During the collisions, the rearrangements between the molecules takes place, which leads to formation of products. This molecular rearrangement usually involves breaking of some bonds and making others. Only when the energy of the colliding molecules is equal to or greater than the minimum energy required for the rearrangement, the molecular rearrangement takes place, followed by the product formation. If the energy of the colliding molecule is less than the minimum energy, then no molecular rearrangement takes place and no product formation takes place. Thus, all the collisions will not lead to formation of products, but only those collisions which involve sufficient energy are expected to form products. The difference between this minimum energy required to bring about molecular rearrangement and the average energy of reactant molecules is known as energy of activation. Higher energy of activation implies strong dependence of rate constant on temperature. As we have already stated that activation energy is the energy that must be supplied to the reactant species so that effective collisions could take place, whereas the minimum energy which must be possessed by the reactants to make collisions effective is referred to as threshold energy. It is important to note over here that activation energy is not equal to threshold energy. In fact, threshold energy is equal to activation energy plus average energy of the reactants. Under normal conditions, the reactant species do not possess the threshold energy required for effective collisions, and therefore activation energy must be supplied. Now, let us look at the effect of catalyst on activation energy. Arrhenius equation states that the rate constant increases on increasing temperature and on decreasing activation energy. One can increase the temperature easily, but reducing activation energy is a difficult task. It can be done by addition of a substance called catalyst. A catalyst will accelerate the speed of the reaction, but will not undergo any chemical change. The catalyst lowers the activation energy by providing an alternative path that avoids slow rate determining step of uncatalyzed reaction, as can be seen. Although the activation energy of a reaction can be calculated from the plot ln k versus 1 upon T, another way of obtaining is to calculate the rate constant at two different temperatures. Now, let us assume a reaction at two temperatures, that is T Kelvin and T plus 10 Kelvin. The temperature coefficient of the reaction is defined as the ratio of rate constant at two temperatures. So, using Arrhenius equation, we get the expression at T Kelvin as ln kT equals to minus Ea by RT. Similarly, the expression at T plus 10 Kelvin becomes ln K subscript T plus 10 Kelvin equals to minus EA upon R within brackets T plus 10 Kelvin. The temperature coefficient then is obtained by dividing the expression at T plus 10 Kelvin upon T Kelvin, where we get the expression as ln K T plus 10 Kelvin upon ln K T equal to EA upon R 10 Kelvin upon T into T plus 10 Kelvin. Or in general, the expression at two different temperatures 2 and 1 becomes ln K2 upon ln K1 equals to minus EA by R within brackets 1 upon T2 minus 1 upon T1. At ordinary temperatures, the energy of activation is of the order of 80 kilojoules per mole. Thus, at 300 Kelvin, the temperature coefficient will have a value of 2.8. This states that the rate constant for a given value of EA increases by about 2.8 every 10 degrees rise in temperature, and mostly this value lies between 2 and 3 only. We will take up more details of Arrhenius equation, activation energy and pre-exponential factor in the next module. So, now let us summarize what we have done in this module. We did study about the difference between chemical kinetics and chemical dynamics. Chemical kinetics is the study of rate of the reactions and factors affecting it. It is an experimental science which studies the reaction at macroscopic scale, whereas chemical dynamics is a part of chemical kinetics which is concerned with the microscopic behavior of reacting species. The ultimate aim of chemical dynamics is to theoretically calculate the rate of a reaction from the knowledge of fundamental properties of reacting species. With this, we then discussed the basics or the fundamentals of chemical kinetics, the rate of the reaction, which is nothing but the instantaneous rate of change of concentration of any of the reactants or products at that time. We did study that rate constant quantifies the rate of a reaction, and the value of rate constant depends upon various factors. We also discussed about molecularity and order of the reaction, where molecularity is the minimum number of atoms, ions, radicals or molecules taking part in an elementary reaction, whereas order of the reaction refers to the sum of the powers to which the concentration terms are raised in the rate law expression. With this, we then studied the empirical relationship between rate constant and temperature, that is the Arrhenius equation, which is of the form K equals to A into exponential minus EA by RT, where A is the pre-exponential factor and EA refers to the activation energy. With this, in the next module, we will talk more about Arrhenius equation, activation energy and pre-exponential factor.